Thanks for staying with me on this series. Looks like there's going to be 6 episodes or chapters where I go from the blank to making these finished ITTP bodies. Well, here I'm setting up the body in reverse 3-jaw on a manual mill for a simple little machining operation, and I'm setting it in rotational alignment. I'm going to use that chisel bladed stop there in a minute to set its rotational position, and I'm using 2 pins to initially set it in the correct position, but this is not the quickest way to use it, a dial indicator on 2 pins. That's a really long-winded way of doing it, and you'll be juggling backwards and forwards for quite a long time. Use the following method. It's much quicker and easier if you put a parallel between the 2 pins. You can do your adjustment a lot more quickly. Once the part's been set in the correct rotational position, we can then use that chisel blade stop to repeatedly place it in position. So we just turn it round until it comes in contact and nip up the jaws, and then each time we're realigning the part very quickly. Have a look at that little adjustable stop there. I've got a video on that little product. I was thinking of including it in the Hallmark product range. You can see there the fitting on the T-slot is using a round T-nut. That allows it to fit a bit like in a V-block, and it will fit in any sized T-slot because it doesn't have to withstand machining forces. It's only a stop. With a T-nut underneath that's rectangular, so it can be turned to suit the width of T-slot that you have, and then it's got the sort of scissor pivot points there to allow you to adjust it to any position, and of course you've got the sliding stop bar on the top. There's a video on that. I think it's called Stops for Mills and Lathes or something like that. Have a look at my playlist. If you're interested in making one for yourself, it could be a good project. I use my little ITTP in a manual machine as well. I've got this simple little attachment that converts it into a manual probe, and I can set up using my digital readout on different features to set your work offset or spindle to work relationship on a manual machine. You can probably see the digital readout up there, so you can set up on a feature very quickly. I've thought about making this as a little product for Hallmark Design as well as that little stop assembly there, but the problem with products like that and that is that they are very simple to manufacture in a low-cost facility. They're really just, this is just in a consumer electronics, you know, a $20 product. The little stop is a similar sort of thing. And you can't really manufacture those in low volumes in a Western country cost effectively. You've really got to think about what your shop is and what you can make efficiently and cost effectively. And I've got a shop that developed on tool making and instrument making and precision engineering, and I can make probes which require high-end accuracy cost effectively, but I can't make low-cost consumer electronics for $20 cost effectively. And I need to keep reminding myself all the time about the importance of looking at the market and the demand before you spend a lot of time developing a product. Of course, that doesn't mean I can't make one for myself and offer it as a design for you guys to make your own one. So there's a simple little product you could make. You could also use a multimeter and just put a little plug on the end and use the impedance feature of a multimeter and just plug that in and use your probe for manual work that way. The cycle time of a machining operation is quite short and is mainly involved in loading and unloading the part, for example in this little job, then often a manual machine is better than a CNC machine because the access is better and you're not bothering with enclosure doors and reaching further into the machine and so on. You probably know a ball nose cutter is a really useful tool to use as a drill in some situations where the depth is not too great and you want the stiffness of an end mill so that it doesn't wander off over intermittent geometry, so it cuts halfway between a drill and a milling cutter. In this situation it's ideal. There's a better look at that adjustable stop there. So you can see the construction is very simple. Two pivoting arms, a little clasp holding the stop rod, all using the same size cap screw, so you only have one size Allen key, and that universal T-slot, T-nut system there, or T-bolt system there, with a rectangular nut that can go either way to suit different size. You might have a couple of different machines with different size T-slots, and that can be universal for them both. I think there is actually a video on this stop with dimensions and a drawing if you're interested in making one as a workshop project. If you don't have a vice stop and are thinking of making a vice stop, this could be a really useful option for you because you can also use it as a vice stop mounted adjacent to the vice on either side of the vice. There's also a small amount of manual work on a part like this where you're chamfering and deburring. I probably won't go into that at length in this video series. It probably needs its own video. Let me know in the comments below if you'd like to see one. I tend to use these three-cornered scrapers, a very small one there and a medium-sized one there, for getting into tiny little awkward places, and also a rotary ball nose bit. You can see a job like this can be quite well done in a manual mill with an automatic tapping head. I've got some M4 threads to do there and tiny little M3 threads to cut in there in these parts, and so it sort of makes sense to float to mount the part on a mandrel that allows it to float into position, and then everything aligns up nice and freely. I'm using a gun tap there. I'm using real-tin aluminium cutting fluid, which is applied with a brush, which also brushes off the chips each time. And then this little tapping head auto reverses when it reaches the bottom of its travel. I've ground a clearance there at that upper shank diameter. Not only is it clear, but it's the thinnest portion of the shank. So I ground down below the core diameter of the thread, right at the top, so that if it ever does break, it'll snap there first, and I can snap on a pair of vice grips and unscrew the tap, and I won't have destroyed the part. So there's a double advantage in cutting that undercut there and there. on that M4 tap, and even more important on the M3, which is more likely to break. Now you're probably wondering, well, why don't you do that on the CNC machine when you're doing the CNC work? Well, there's a couple of reasons. One is it's very quick and easy to do by hand, floating it in on a mandrel like that. The other one is you can apply cutting oil, which is better than a water-based cutting fluid, and you can better control the situation. You're much less likely to have a breakage, and you really want to avoid a breakage. The operation is really fast, and I can run through these parts very quickly, really. And so I think for very small threads, it's worth considering using a tapping head. I think I did a video recently, you can see in the playlists, tapping heads for tiny threads or something like that, where I go into this in more detail. Well, now I've done all the M4 threads, I'm going to do the M3 threads, which is probably many times more fragile. You can see I've ground the shank down there to about 1.5 millimeters diameter, so that if I get a breakage, it's a safety backup. I can snap vice grips onto the stub and remove the tap without destroying the part. I've also got the clutch set very low, so that should slip before the tap breaks. I really don't want to break a tap at this stage of the part and have to bin it. So there's three M3 threads to be tapped. One of them is right through into that gland hole, and the other two are blind. And I'm using gun taps or split point taps because they put the least torque on a tap out of the commonly available taps. A machine tap for a blind thread, or a gun tap, or a split point tap, or a plain hand tap. The gun tap is probably the best for this situation for very small fragile threads. The problem with it is that it throws the chip ahead of the tap. And in a blind hole, you've got to spend a few seconds hooking out the chips with a little piece of wire and blowing it out with kerosene and compressed air. But I'd rather pay that price of time than break my machine tap. They're expensive and they destroy the part, and they take more torque because they've got to pull the chips back up out of the hole. The flutes have to be ground away bigger, and so the whole tap is more fragile. So I use a bit of very small diameter spring wire with a hook on the end there, just to catch the little bits of chips in there and pull them out and blow it with compressed air and kerosene. Another option with blind threads is to use a hand tap, a hand bottoming tap, and that pulls more of the chips up into the flutes and you've got less fishing out to do. But in this case, because that thread is deep and can go right through, a gun or split point tap is ideal because it pushes the whole chip down out of the way. And finally, the polishing stage. Some of them get a bit scored where the swarth rubs against them when it's spinning in the lathe, and other little scratches and handling marks and so on. And so I run them through that process using a curved board. That way it keeps the wet and dry paper in peripheral contact with the part. So if you were just to put it on a flat surface, it would produce an uneven polish. This way it keeps the profile correct. because that's a close fit on the actual circumference. And a bit of a polish up on the flat surfaces and so on, and I wash it in this, wet it and wash it in a bucket of something like car wash. It's just a detergent basically, and then blow it off with compressed air, and end up with a nice surface finish, removing those which are very shallow swarf scratches and so on. Get a nice surface finish ready, and a rough clean ready for anodizing. And the final product coming out of anodizing, well, I've also put the gold enamel in there, but it's a really nice finish. I think they run it through a acid bath to etch it slightly anyway, but you know, you need to get the major scratches out before you send it away for anodizing. Well, that about wraps it up, guys. I've finally finished this run now of bodies, and I can send them off for anodizing. Hopefully they'll come back like these parts did last time. Just got to do the final gold enameling, and then I can assemble up another batch of Hallmark impact tolerant touch probes, a mixture of 12mm and TTS shanks. Well, thanks for watching me through this series. I've enjoyed making it. I like sharing things with you out there. I'm in quite a remote part of the world in New Zealand, and I don't have a lot of contact, so it's really great being in contact with the international manufacturing, engineering and hobbyist community. Please don't hesitate to send me comments or even emails. I love to hear from people around the world and feel connected with them. If you found something useful in this series, make sure you like and subscribe. That way you'll be notified in the future when new videos come along. Alright, thanks guys. Catch you next time. Cheers.